Okay, now in this session we'll be seeing about the activation layers. So different activation layers, okay, we will be seeing in this. So we have seen in the various lectures that how the activation layer works. So consider this is your node. We have the inputs like x1, x2, and x3 for that matter. Okay, so this is the input that is applied to the node. Okay, and what is also applied is nothing but the bias, that is +1 is the bias. Okay, so this is being applied, and also along with that we'll be applying the weights. So we can apply W1, W2, and W3 are the different weights that are being applied to this. So what we get is W transpose of X plus B. Okay, so this is nothing but my Z. Now this output Z is actually to this we are actually applying the activation function. Okay, so activation generally we are taking sigmoid as the function. So this will give sigmoid of Z is nothing but the output A. Now this A is nothing but the output that is generated after applying the sigmoid function to the Z. Okay, which is nothing but equal to y hat. Okay, so this was what we had seen in the previous explanation or previous various lectures also. So you can say that the if there are multiple such layers, okay, you can say like now these activation functions are usually applied to multiple such layers. So for example, for the first layer, okay, okay, of input X, so the output that is generated is Z1. So W1, okay, into X plus B of 1. So this says that the W weight is applied to the weights that are applied to the input in the first layer, and what we get is nothing but the output. To the output we are actually applying the sigmoid function, that is sigmoid function that is applied to Z. It will give you A1. Okay, same way Z of 2 is nothing but output that is generated, that is second time, that is from hidden layer. Okay, and the weights, the output from the hidden layer which will become input to the output layer. Okay, in the second layer of the neural network. Okay, so it will be, this is nothing but X, and the set of weights are nothing but W2. So W2X plus B2. Okay, because the biases are applied to the second layer of the neural network. So this will give me Z of 2, and what we calculate is A of 2, which is nothing but the sigmoid function that is applied to this. Okay, so to this we can see that for both of these things we are actually applying the logistic regression. So logistic regression, that is applied to hidden layer, and the logistic regression to the output layer. So in hidden layer, in output layer. Now since we are discussing about the activation function, so here you can say that this is x1 and x2 and x3. When we are applying the inputs, okay, to these different nodes over here, okay, the outputs and that is generated is for that output we are applying the activation function. Okay, and what we get here is y hat. So here you can say that Z of 1 is nothing but equal to W1 X plus b of 1, and a1 is nothing but the output that is generated. Okay, for that the activation function is applied. So that is what I was telling, sigma z of 1. Okay, and the z of 2 is nothing but the output that is generated for the second layer. So w2 of x plus b of 2. Okay, where a of 2 is nothing but the sigmoid function that is applied to z. Now, not necessarily that the you have to apply forward propagation during for we use sigmoid functions. So we can avoid this. So we can, instead of sigmoid function always telling sigmoid function, we can gen we can say that an activation function is being used. So we can give the notation as g of z of 1. So this will give a generalized thing that we can give any activation function like by mentioning it as g of z of 1 and g of z of 2. Now, till now we had seen about the sigmoid function. So sigmoid functions, what does a sigmoid function explain? A sigmoid function, okay, is nothing but this is my 0 to 1, okay, where you can say that if my z value is you can say negative, okay, if it is negative, then my a value, okay, will be actually in the 0 region. Okay, so the my a here a is equal to 1 by 1 plus e power minus x. So if my z value is negative, okay, so my a value that is, if my output is negative, so if I'm applying sigmoid function to my output value, if I'm applying output function to the sigmoid function to the output value, then it will be tending towards the 0. The moment my z value is positive, then my a will be can say will be tending towards 1. So you can say that this is what you can say. So this is my the moment my z is tending towards 1. Okay, so z is a positive value for that. So this is a negative value. This is once it is a positive, it will be tending towards a, okay, the output will be tending towards the 1. Okay, so sigmoid function is always between, okay, function is between 0 and 1. So the a what you get, okay, should be between 0 and 1. Okay, so the activation function goes better than uh, the sigmoid. So sigmoid function, that is nothing but the tan h function, or you can say tan h function equals the hydraulic tan h function. So what is that tan h function? So this is another activation function which you can see here, or you can say hydroponic tangent function. So hydroponic tangent functions, or you can say, consider this is the one, z is -1 to +1. This is somewhat, you can say, a mathematically shifted function to sigma. So we can say that we have, okay, a curve like this, so which is ranging between -1 to +1. So because it is ranging from -1 to +1, so you can say that a, which is nothing but the tan h applied to the z, okay, which is nothing but e power z minus e power minus z divided by e power z plus e power minus z. Okay, so here what we are doing here is in the tan h, it crosses my 0, 0, okay, point, that is it will go from -1 to +1. Now this actually performs better than the sigmoid function. because the mean of this is actually, if I are taking the mean between the mean of -1 plus 1, so it actually comes in this region, point only. But if you're saying in the previous case, the mean is actually coming in the 0.5 region, somewhere in the 0.5 region. Whereas you can say that the mean of this actually is coming around like 0.1 or 0.2. So here also it is minus 0.1, 0.2. So it is coming near to 0. Here you can say that it is going away from the 0, but in this case it is coming near to 0. That is the reason why tan H is performs better, okay, than sigmoid function. It performs better than sigmoid function because the mean of that is being taken in this case, okay, will be the near to 0. So we can represent this as g of z, or I can say equal to tan h of z of 1. So normally this tan h is applied to the hidden layers, but not the output layer, because for output layer, okay, you should have the output between 0 to 1, but the tan h is usually between -1 to +1. So to avoid this kind of thing, for the output layer, so in output layer the preferable will be this sigmoid function, but for the hidden layers, okay, we'll be using this, okay, and for the output layer we'll be using the sigmoid, okay. So this is about the tan h function, okay. And when you're applying, so this is the network where you are having x1, x2 and xt. So this is my nodes normally. So I can apply tan h here, okay. A tan h can be applied as an activation for the hidden layers. So this is a sigmoid function, and what I get is equal to y hat. So the equation can be written as g of z of 1 is equal to tan h of z of 1, and for this I can write it as this is nothing g of 1, so I can write it g of 2 z of 2 is nothing but equal to sigmoid of z of, because for the output, okay, we cannot use tan h because as I said, tan h is ranging between -1 to +1, but for the output we require output to be either 0 or 1. That is why it is preferable in this for this particular thing we will be using the sigmoid function, okay. So this is about the tan h and sigmoid. Now the other thing, another the activation is very popular, that is nothing but the RELU, okay. The RELU is also known as the rectified linear unit, okay. Now how do you represent this? So representation of RELU is somewhat like this. You can say that uh, now this in for the z, okay, this is my z and this is my nothing but the a, okay. So the output that you are getting, even if your output is a negative, okay, like 0.0001, so you can say that this is my, okay, even it is a 0.0, so it will be tending towards 0, and that A is will be tending towards 0, and the moment it is positive, you'll get a sharp curve like this. So this one you can say that here A is equal to max of 0 comma z. So what does it say is that if your z value is 0, okay, any z value that is 0, or even if it is a negative value also, it will be your A will be 0. So A will be 0 if it is a if your Z value is some negative value, and it will if it is a higher Z value like positive Z value, okay, then it will be a, you can say, sharp curve will be there over here, which will be tending. So there is not a curve just like a sigmoid function. So it is a sharp line, okay, which will be your A value. So any positive value, it will be have a it will be tending towards the A. Okay. So if output is somewhat is 0 comma 1, so in binary classification, the sigmoid activation function is very natural choice. So that is, if you want output ranging between 0 comma 1, okay, then the sigmoid is preferable. Then for other things, okay, you can use RELU activation function. So RELU is actually is preferable for the hidden units than the Tanh. Okay. Now why it is so because RELU is, if RELU is 0, okay, if your Z is negative. So even if your Z is negative, then also your RELU is 0. And unlike in the sigmoid, you are having the curve is somewhat like this. Okay, we have this straighter line over here. Okay, in RELU. So another aspect in the RELU is nothing but the leaky RELU. Leaky RELU is one more thing which is more preferable. That is, even if Z is negative, okay, then leaky RELU also will be negative. That is, your A will also be negative. That is, in here you can say that the graph will be somewhat like this. So even if it is negative, so we can also keep our output a slight negative in this case. Okay. So to sum it up, okay, so sigmoid curve is like this. Okay, where I can say that if it is a negative, if your Z value is negative, it will be, okay, tending towards 0. The moment it is positive, moment you see that when it is 0.1 minus 0.1, it will be coming to 0.5 region. The moment it is positive, it will be coming towards the 1 region. So this is my A, this is my Z. So A is equal to 1 by 1 plus e power minus Z. Same way, tan H is the extension to it. So hyperbolic tangent function. So this is the hyperbolic tangent function, which is an extension to a sigmoid. Okay. The only difference here is the value here is the tan H is nothing but A is equal to e power minus Z minus e power minus Z, e power minus Z plus e power minus Z. So the value A here ranges between -1 to +1. The A value ranges between -1 to +1. Okay, and this is more better than sigmoid because the reason being the mean value, if you take, will be near to 0, near to 0 here in this. Whereas in sigmoid, if you're taking sigmoid, the mean value will be somewhat near to 0.5. Here it will be less than 0.5, somewhere 0.1, 0.2. We can have a mean. And ReLU is denoted as, so this is a sharp thing and this. Okay. So the equation for ReLU is uh, A is equal to max of 0 comma Z, and your leaky ReLU, yes, Okay, this is my leaky RELU. So equation for leaky RELU will be max of, okay, 0.00, okay, 12 comma z. Okay, so this is how your leaky RELU is all up. Now, so if you have any query regarding this, okay, you can ask. Okay, so thank you so for patiently listening to this. Okay, thank you.